Let me give up on this thing. Oh, here we go. And that's fine. All right, so this is a very similar graph here, again, showing the amount of water per time, cubic feet per second. But now I'm breaking it up by the tributaries of Lake Champlain. And this is really to show that the top biggest 5 tributaries in the storm contributed 80% of the water over a 7-day period. So this is really a storm of our major tributaries, the Winooski River, the Moyle River, Missisquoi River, Otter Creek, and the Saranac River. They contributed 80% of the water of this time period compared to the other 13 tributaries that we're looking at here. So total of 219 billion gallons, 829 cubic meters, a couple different ways to say it's a lot of water as a result of the storm, historic amounts of water. Here's a photo I took near where I live in Essex Junction, looking downstream on the Winooski River. And I have some stats here going back to 1990. So for July 11th, the daily average flow was greater than the 90th flow percentile for all of our tributaries. It was the highest ever recorded daily flow for the Moyle River going back to 1990. It was the second highest ever for the Winooski River, second only to Tropical Storm Irene. And it was the highest flow ever for this date, going back to that question, for nearly all of our tributaries. It was second for only for 2 of them. So I'm going to come back to this theme a couple times. But this was really unusual for this time of year, for the summer period, when typically our rivers are running a lot lower. We don't have these big storms like this, really cranking out a lot of water. All right, here's another crazy graph for you. This is a total measured water flow, again, to Lake Champlain for 17 rivers all added together for all years since 1991. And we're starting on October 1st here because we're talking about something called a water year. Anyone ever heard of a water year before? Or a fiscal year? Okay, it's basically a fiscal year, but it's for water. Okay, so it starts on October 1st and it ends on September 30th. And we do that because we don't want to break the winter into 2 different years. Okay, so that way we're starting in kind of a dry period, going into the wetter fall and the winter, and then we end it again in the fall. So starting on October 1st here, every line is an individual year. And it goes up and down, based on what the water is, how much water is flowing to Lake Champlain. You can see it's really variable going up and down for all these different years. And that's why we have an average line where you see it's highest usually in the springtime. This is March and April and May here, when it's usually the highest. It's the average that we might see. So now I'm going to highlight 2023. So here's 2023, and you can see this is the peak here. This is the July flood, highlighted in purple pink here, and you can see it's really high, but it's not the highest it's ever been. And actually it's the 13th rank it's ever been, going back to 1991. The other highest flows are typically in the springtime or in the late fall. And this one here is, I'm going to highlight 2011 now. The highest ever is from Tropical Storm Irene in the blue here. And 2011 was, as you probably know, really unusual year because we had incredibly high flows in the spring and then again in the summer. And we're going to come back to that idea a couple times. And now this is a really similar graph, but kind of focusing in on the spring and summer period. And just to show that this 2023 is really standing all alone here because it's so unusual to have flows this high in the summer. The other times when it's been up in this region of this much flow has been in the spring period for other years going back to 1990. And again, here is 2011 Tropical Storm Irene. So especially high for this time of year. The average flow is about 7,000 cubic feet per second for this time of year. And again, we're going up toward about 110,000 at peak flow cubic feet per second. All right, now I'm going to provide some context for how the distribution and timing of water being delivered to Lake Champlain is changing since 1990, when we really started looking at this closely, or had the funds to monitor it, and how this is being affected by climate change. So this is a totally new type of graph I'm going to try to explain to you here. This is the Winooski River discharge, again, the amount of water moving downstream and how this is changing over time. The vertical axis is the trend in the whether the trend over time is increasing or decreasing. So it's increasing if it's above this horizontal line, and it's decreasing if it's below this horizontal line. And the horizontal axis here is called the flow quantile. So the highest flows are all the way to the right, and the lowest flows are all the way to the left. So this is showing that the kind of higher flows of the 75th to 80th percentile for the Winooski River are really increasing over this 30-year time period. Okay, so we're seeing increases for the Winooski River over time. And now I'm going to show the same thing, but broken up by season. And this is showing that in the summer, we have increasing flows over this time period in the summer throughout the low flows all the way to high flows. And our highest flows are really increasing at about 2% per year. And in the winter, we also have increasing flows. And what this is really showing is the signature of climate change. We have more precipitation falling as rain rather than snow, which is giving us higher wintertime flows compared to earlier. I'm not showing this, but we also have lower flows in the spring because more of that precipitation is falling and running off quicker rather than being stored in the snowpack. And then in the summer, we're seeing more of these episodic big rainstorms that are bringing larger floods over time. Okay, so just want to show you some context of how our flow is changing due to climate change. All right, next thing, that was all just water, right? Rain and the water moving through our rivers. Now I'm going to talk about phosphorus delivery. And phosphorus is an incredibly important nutrient for water quality because it drives things like cyanobacteria blooms and really the ecosystem of our lake. So it's important to track and understand. So phosphorus delivery. Well, I also should have mentioned that these amazing aerial images are captured by Peregrine Productions, is a videographer firm that we've worked with, and they sent up some drones and took some amazing imagery that I'm featuring here. Okay, so this is a really similar graph to what I showed earlier, but this is for phosphorus delivery. And again, I'm breaking it up by the different tributaries to show that, first of all, on July 11th, 175 metric tons of phosphorus was delivered on that day. A metric ton is about the mass of an African black rhinoceros. Okay, so imagine that in the room, that's what that 1 metric ton was. So imagine 175 of those moving downstream, that much phosphorus. We'll talk about whether that's a lot or a little in a few minutes. But for the over a 7-day period, again, the top five rivers, the Winooski River, the Missisquoi River, the Lamoille River, Otter Creek, and the Pike River together delivered 90% of the phosphorus for the 7-day period. Okay, so just 5 rivers are delivering 90% of the phosphorus, the most important for the storm. Yeah.
How is this measured?
How's this measured?
Yeah.
That is the longest side I can go down, but briefly, we have the amount of water. And as part of our monitoring program, we go out and collect water samples to measure the phosphorus concentration, it's called. So how much phosphorus in a bottle of water per liter. And from that, we can do some math and statistics and modeling to predict how much phosphorus is moving downstream. Once you estimate the concentration in a river, you can multiply it by the amount of water and estimate the mass of phosphorus moving downstream. That's a really brief overview of how it works. Yeah.
Just following up on that, does the proportion change, the concentration change during an event like this?
Rapidly, yes. That's actually the subject of my PhD dissertation, is how that happens. So yes, it rapidly changes over the course. It can change by the minute, actually. So what we're doing is a pretty crude estimate on a daily basis of how much phosphorus is going downstream to get us an annual estimate. But it's amazing how dynamic these systems are. And when it starts raining, it's like a chain reaction of all these things happening, and the phosphorus is being moved to the river and then downstream. And the more you look, the more dynamics you see. So, yeah.
Does this have to do with how much agriculture is in the river basin?
It is
that where the phosphorus is coming?
It is related. So all human activities in our landscape will be contributing phosphorus in different ways. As a whole, for the Lake Champlain Basin, an estimated about 40% of the phosphorus does come from agricultural activities, and 60% comes from other things, developed lands, wastewater, stream bank erosion, things like that. So topic for another talk, but yes. All right, so I'll keep moving on this here. So over a 7-day period, the load to the lake was 359 metric tons of phosphorus. And oh boy. going back to the TMDL, the annual budget, what we're aiming for. This was about 62 to 85% of the annual load that we're shooting for. So that's a lot, right? In 7 days, we delivered more than half of the annual amount that we're shooting for. This is a major event, and we'll talk more about that. So it's not unusual that storms like this will deliver a sizable portion of the annual load, but this is, more than we're hoping for sure. So some stats on daily phosphorus loading. It was greater than 90%, 90th percentile for all of our tributaries for that July 11th daily load. It was the highest daily load ever for phosphorus delivery for the Pike River. It was the second highest load ever for the Winooski River. It was the highest load ever for this date for all but 2 tributaries. Again, going back to how unusual this is for the summertime for mid-July. It was the 3rd highest daily load of phosphorus ever delivered to Lake Champlain. The highest was Tropical Storm Irene, and the second was the Halloween storm of 2019. Who remembers that one? Yeah. Yeah, my family lost a part of our roof in that storm, so we remember that very well. So that was actually the second highest amount of phosphorus ever delivered to the lake. This storm actually came in 3rd place since 1990. So I found that pretty interesting. Okay. Again, putting this in context, this is going to be a new type of graph again for you, and just enjoy this image for a moment. All right, so this is similar to what I showed for the amount of water moving into the lake. This is now the cumulative phosphorus, so we're adding up the amount of phosphorus as we go. We're starting at the beginning of the water year, and every line is a different year again, and the average is shown in yellow. So we're looking at the metric tons of phosphorus vertically, and you can see for any given year, any line here, the rivers are contributing phosphorus and the line is just ticking up as the year goes along, right? So when you see a jump, that means there's a storm, essentially. And if it's kind of checking along horizontally, that means there's a lot of days without a storm. And then when the line jumps up again, there's a storm. Okay, this is all the years since 1990. I'm going to highlight 2023 now. I'm going to try to, there it is. So the interesting thing about last year is that in the springtime, we were well below average. I almost didn't remember this until I started looking at the data, but we had a really dry spring. And the summer was so wet, it was easy to forget, but the spring was very dry and we were well below average going into July. And then when we had this massive storm, it jumped, the cumulative phosphorus to Lake Champlain jumped way up, way above average, but it did not jump so high that it was totally out of line with what we've seen historically, because we started off a bit lower last year. And now if you compare this to 2011, very different story, right? We had storms right off the bat in October that jumped us up way above average for the beginning of the water year. We had huge flooding in the spring that was historic and caused lake shore flooding and huge damages along the shoreline and in the Richelieu River in Quebec. And then again, Tropical Storm Irene sent us into the stratosphere for 2011. So really interesting comparison. Last year, we had this historic storm, but we were coming from below average for phosphorus delivery. And then in 2011, we had just big storms throughout the entire year. So very different years. All right, now I'm going to show very similar graphs, but I'm going to break it up by different segments of the lake, because every lake has its own goal for phosphorus delivery. It has its own budget. So Missisquoi Bay, the main lake, Mallett's Bay, they all have their own goals for how much phosphorus we're trying to limit to in those areas. All right, so now we're looking at Cumberland Bay, Main Lake, Mallett's Bay, and Missisquoi Bay, but very similar graphs here showing the average in yellow, and then every line is an individual year. I put a new line on here, which is the goal of the TMDL allocation. This is what we're shooting for. We want to stay below those orange dotted lines. Now I'm going to show, I'm going to show the 2023 line here. Cumberland Bay is at the mouth of the Saranac River. So you saw how this was not a historic event on the New York side. We did not see a huge amount of phosphorus coming into Cumberland Bay. There's not a big jump in phosphorus around July. So we're still below, we were below average and below the TMDL on Cumberland Bay. Compare that to the Main Lake. We were below average and below the TMDL, and that storm jumped us into second place for our record, for the record. Mallets Bay, similarly, we were below the TMDL, below the average, and that storm, put us above both. And same thing for Missisquoi Bay here. We're usually, Missisquoi Bay is where we're furthest above our TMDL target. So almost every year, we're above that target, which is why it's the focus of so much restoration effort. And here we were above the TMDL, but below average, and then it jumped us above both of those. Connie?
Yeah, Matt, when you're ready to pause, maybe we can just ask how many people are on the west shore versus the east shore of the islands? Or anyone up in Albert by Missisquoi Bay? Just a show of hands. How many over here face the inland sea? Wave to me in the morning on the Georgia Shore. Okay. How many of you walk to sunset over in the evening? Okay, thank you. I was always curious for the breakdown.
Thanks, Connie. Yeah.
Is Keeler Bay considered part of the inland sea, considered part of the main lake?
That would be part of the northeast arm.
Okay.
Yes.
I'm sorry, I didn't hear what?
Keeler Bay would be part of the northeast arm segment.
Which locals may call the
Inland sea, yeah. Yeah, there's a number of different names and how you can define it, but yeah, inland sea, northeast arm are similar.
So the main lake is that section of the inland sea is considered part of the main lake for monitoring purposes.
No, it's separate.
Okay.
Yeah, and we can combine them and break them up in different ways. So in some cases, I'm talking about the whole lake.
Yeah.
In some cases, I'm talking about separately. I don't have Keeler Bay represented here. One of the challenges of that area is we have less monitoring of our tributaries going to the northeast arm, inland sea areas. So it's not represented here because I'm not able to characterize it quite as well. Okay. So, yeah.
I just had a question about how much, like, if we had no sediment going. If the water coming out was clear, would you still be carrying a lot of phosphorus, or does the sediment carry a big proportion of it?
Yeah, great question. So if we could magically remove the sediment, that would remove a good portion of the phosphorus. So phosphorus comes in many forms, many flavors. The two big buckets are particulate, so the phosphorus that's kind of, it's called adsorbed, or kind of glued onto the sediments, and it kind of hitches on for a ride and goes downstream onto a piece of, small piece of sediment, sand, silt, clay, and those can be broken off and become dissolved and can be used for something to grow in the lake. There's also the dissolved phosphorus that's not hanging onto a piece of sediment, and that is already more available for something to grow. So yes, reducing erosion and the amount of sediment going downstream is a big part of reducing phosphorus overall. We can never eliminate it. Sediment erosion and sediment delivery is a natural process for all rivers, and we wouldn't even want to reduce all of it. But it is, a focus of restoration to try to reduce as much as we can.
So, but do you have like some idea of what percentage is on the sediment and what percentage is just floating in the water?
Yeah, so for the Winooski River, it can range from 30 to 40% dissolved, and most of it will be particulate. Yeah. All right. Okay, so again, highlighting 2011, so very different. We had, once again, much higher loads earlier on the year, and then summer storms shooting it even higher. So same story for that. Okay, I'm gonna skip this part because we're a little lower on time, go right to here. So this is a concept again, to put it in context. So high flows are always important for nutrient delivery. And this is a bit going back to your question about, particulate phosphorus. Whenever we have a rainstorm and a lot of water moving downstream in a river, we also have higher concentrations, going back to the question, I can't remember who it was from, but about how we measure these things, or how we estimate, it's yours, right? How we estimate these things. So we have a higher concentration, more phosphorus in, say, a bottle of river water, and more water in general. So it's a multiplicative effect. So when we have storms coming through, it's really a disproportionate amount of phosphorus moving downstream. So this is kind of a cool graph showing this idea. So here we have the portion of phosphorus contributed by the Winooski River, and each color shows a period of time. So, and this is from 0% all the way to 100% or 1 here. And this is showing that the biggest single day of phosphorus delivery in yellow here contributes about 5 to 10% of the annual phosphorus load. So the biggest day on a typical year will send 5 to 10% of phosphorus for that entire year. The biggest 5 days usually send about 20% of the phosphorus for the entire year. And the biggest 30 days typically send about 60% of the phosphorus over this entire year. So that means the remaining 335 days, I think it is, send 40% of the phosphorus. So this is just demonstrating that storms are always an important time for when phosphorus is moving downstream. Last year was no exception, 2011 was no exception. For these big storms, we just have a lot more happening in those few days, and that's why they're so important. Yeah.
Question I had was if a flood is like flushing a toilet for the river basin,
I wouldn't put it like that.
the higher flow,
Yeah.
do subsequent floods as that landscape gets cleaned, do subsequent floods, which with climate change, we seem to be in a pattern where we're gonna have more and more floods.
Yeah.
Are they gonna move less phosphorus if we stop putting phosphorus in the river basins upstream?
Yeah, so in the long term, yes, that is the idea, is that we want to reduce the amount of phosphorus kind of available to move during these streams. Unfortunately, a lot of our areas are so saturated with phosphorus that we're not at the point where they're able to be, I guess you put it as clean, but
Yeah.
that we're depleting the phosphorus. There's so much built up in sediments. We call it legacy phosphorus, phosphorus that's been deposited on agricultural landscapes or in cities. It's out there, so when these storms are coming through, there's a lot for it to move to our rivers and to the lake. So we're not to that point yet, but that is the long-term goal, right? That's what we're aiming for. And we do have studies to look at that long-term, we call it a mass balance, or how much is moving in, how much is moving out, and can we get to the point where we have more of a balance of phosphorus so that we're not continuing to, build up that legacy. So great question. All right, I'm gonna talk about some fun monitoring here. This is a water quality monitoring buoy, and this is in the Lamoille River under the Route 2 bridge. So we deployed this, this is our second season running, and this measures water quality every 15 minutes. So getting back to, this is your question, does this change over time during a storm? When you measure it every 15 minutes, you can really see the dynamics over a 7-day period or over even a day. So this is a pilot program. We have a website, data.lcbp.org, where you can see data on the internet in real time for the Lamoille River and through several locations in the lake. And during the storm, we lost contact for this buoy. It went under. It's secured by an anchor at the bottom of the Lamoille, and that was holding it down as the river went up. And we didn't know if it was still there. We were pretty worried about it. And then a few days later, the river, the flood waters receded. It popped back up and sent us all the data. It was measuring the water quality underwater the whole time. It worked beautifully. So I'll show you some results from that. Here on the top, we have discharge, your volume of water moving downstream from the Lamoille, cubic feet per second. The pH is a measure of how acidic the water is. So this is all within the normal range. You might remember this from chemistry class, right? Rainwater has a lower acidity than base flow or groundwater. So that's why we see the pH drop over time. Specific conductivity is a measure of how many things are dissolved in the water, getting back to your question of dissolved versus particulate. So you can see this drop over time. So some really interesting water chemistry going on. But the thing I really want to show is the turbidity. The turbidity is a measure of how turbid, how murky the water is, or how not clear it is, right? So the higher it is, the more murky it is. So we're really looking at something that looks like chocolate milk at the top of the peak of the storm. Really high turbidity spikes here, and this gives us an estimate of how much sediment was moving downstream to the lake. I'm gonna come back to more buoy data toward the end of this, but now I'll talk about lake level. So that was really all tributaries, our rivers, right? What was going on with the watershed moving downstream. Now I'm gonna talk a little bit about the lake itself. And starting with lake level. So this is a similar type of plot as I've shown before. This is Lake Champlain level measured in Burlington in feet above sea level for all years going back to 1907. So every line is a year, again, starting at the beginning of the water year. You're pros at this now, right? The yellow line are the average for all of our years going back over 100 years. So you can see obviously in the springtime, that's when we have our highest lake levels, and then it goes down, typically down throughout the summer, right? Now I'm gonna highlight 2023, last year. So we had a very typical spring. And then, as I said, we had a dry, during snow melt, and then later in the spring, it was pretty dry, so lake level dropped to below average. We had a few small storms before the big one, and so we were at pretty much right at the average lake level right when the storm hit. So we went from average to 3 feet above average. Lake level rose 3 feet as a result of the storm, which is amazing. The lake has a surface area of 435 square miles. All of that area rose 3 feet. So just imagine that volume of water. It's amazing. Now I'm going to highlight 2011 again. Totally different story. Once again, historic or highest level we've ever seen, over 103 feet above sea level. Flood stage for this datum is 100 feet above sea level. So this is the historic spring flood for 2011. And then it went down pretty close to average throughout the summer. And then Tropical Storm Irene also raised the lake about 3 feet. So very similar effects on lake level, but later in the season there. So both storms rose the lake about 3 feet. Now, looking at lake water quality, these are photos from Mallett's Bay at our long-term monitoring station. This is another monitoring buoy you see out here. The Secchi depth, does anyone know what Secchi depth is? All right, nice, okay. So Secchi depth is another measure of how clear the water is. So this is a very old method going back to the 1500s. It's essentially a dinner plate on a rope. So we drop a dinner plate in the water and we measure the depth at which we can no longer see the dinner plate. Okay, it's a very simple measure of water clarity. And typically in Mallett's Bay, it's about 2.5 meters. Okay, on July 20th, about a little bit more than a week following the flood, the Secchi depth was 0.4 meters. Okay, and this is important for something called a photic zone. Photic zone is the depth of water that light can reach for photosynthesis. So there's always things growing in the lake, forming the base of our food web. We call them our primary producers. So when that photic zone, goes from, and the photic zone, I should say, is about 2 to 2.5 times the Secchi depth. So imagine typically it's about 5 meters deep, but then it went down to about 1 meter. So it's a 4 meter reduction in photic zone. So all that primary production or photosynthesis is being suppressed and reduced as a result of the storm. And this took about 2 weeks to recover. So we had a much more murky water essentially than normal that you probably noticed if you're looking at the lake at this time. So this is a photo of the monitoring buoy in Mallett's Bay. I'm going to show some data from this. So again, back to this turbidity, how murky the water is, right? So typically this is really low in Lake Champlain, especially Mallett's Bay, very clear water, low turbidity. And then when the storm, the sediment plume, essentially the murkiness reached this buoy, it shot up to almost 30 units of turbidity here. And then when that first plume kind of settled, it went down, and then sediment from other rivers mixed throughout other parts of the lake, and it shot it back up. So really interesting dynamics that we're now capturing with this new monitoring system. Now I'm going to put it together from the Lamoille River. So the Lamoille River, empties into Mallett's Bay. See, it's a major tributary from Mallett's Bay. Here again is the discharge, the amount of water moving downstream from the Lamoille, peaking right here on July 11th. This is the same thing you saw before, the turbidity for the Lamoille River, spiking really early in the storm, and then going down and then rising again toward the peak of the storm. And then it took about 2.5 days for that sediment plume to reach the Mallett's Bay monitoring station, which is about 2 miles away. So a little over, about a mile a day or so for that sediment plume to make its way out to the lake. So really interesting, useful information here from these monitoring buoys. That's summary. All right, I'm going to quiz you all. For rainfall, we had historic amounts of rain, 3 to 9 inches over a 48-hour period. For river flows, a greater than 90th daily flow percentile for all of our tributaries, a record, daily record for the Lamoille River, and second place for the Winooski River, historic amounts of water. Unusually, especially unusual for this time of year in the summer, and consistent with what we're seeing for climate change trends, where we have more of these extreme events, more persistent and frequent rainfall events like this. For phosphorus delivery, it was preceded by a very dry spring and relatively low phosphorus delivery going into the storm. 5 of our tributaries delivered 90% of the 7-day storm flux, we call it. And more than half of the full lake annual total maximum daily load was delivered in a 7-day period, which is really significant. This is especially important for the main lake, which is where the Winooski River, flows into. And the Winooski River was really a driver for this event. It was incredibly active. And this also was consistent with climate change trends, especially for the time of year. Lake level rose about 3 feet from average level to a record high for the season. I forgot to mention July 23rd, we hit a record for that date. So it was the highest that the lake has ever seen on July 23rd. So really unusual for that time of year. But it was near normal for a springtime. So if it were spring, it would have been a normal level. For summer, it was very unusually high. For lake water quality, we had very high turbidity as a result of the storm. Primary productivity, that photosynthesis was likely suppressed or reduced. Dissolved nutrients were likely available for later season growth. We did have short-term bacteria impacts. I didn't talk about that earlier, but because of some untreated wastewater that was, made its way to the rivers, we did have some bacteria impacts, but this was not widespread. It was mostly focused in the mouth of the Winooski River. For 2023 data, we just have this approved. I didn't have it ready to show you tonight, but if there's questions on that, I can get to it soon. I don't want to take up too much time here. I don't have time for your questions. I want to talk a little bit about restoration. So the TMDL, the target we're going to for phosphorus, does have something called a margin of safety. So it does take into account things like climate change and big events like this. So there's going to be an interannual variability, just a way to say that some years are really wet and we have a lot of phosphorus moving downstream, and some years are relatively dry. So what we're trying to do is bring the trend downward. We're always going to have that variability where one year's high, one year's low, but in general, we want to trend downward so that on the whole, overall, we're getting closer to our goals. This storm is a signature of climate change where we're seeing more persistent rainstorms, more frequent rainstorms, and the summer extremes are higher, the winter flows are higher, and spring melt is generally lower. And we're working on building resilience toward for these storms for our communities. We had a lot of examples of where things that were fixed or updated or upgraded since 2011 held really well during this storm. There was a different extent of where the storm hit. So some areas that were not hit hard in Irene were hit hard in 2023, and that kind of showed where the infrastructure was damaged. And so we're learning on how to make our communities more resilient. And I think that's all. So we have a summary of the 2023 flooding on our website. I have a link to the real-time data that I talked about. We have a science blog, Lake Champlain Basin Program science blog, where this is really for folks who are engaged in these topics to learn about the research that we have going on, really short articles to see some of our main topics. This is another historic photo from 1927 in Springfield, Vermont, the Great Flood of 1927. So that's what I have for you. Thank you.
Yeah, the storm from last July, why doesn't it have a name?
Well, I think NOAA tried, what does it not have a name?
Yeah.
So NOAA has called it the Great Flood of 2023. So you can call it that if you'd like. Yeah.
Have you tried to compare the forecasts by whatever weather system, right,
Mhm.
to the amount of water that was actually measured through the flow and through the lake level?
Like going back and seeing how accurate the forecast was?
Yeah.
I haven't. That seems like something that the weather service would like to do, probably. Yeah, I'm not a forecaster, so what I saw was what I was really glued to was the projections of the river stage that I showed, like how will the rivers go? I found them to be really useful and really accurate. They do get adjusted as you go. But I have not personally gone back to see if what they projected for rainfall was accurate or not.
I mean, it's still the forecasters who warn us
Right,
about potential problems
yes,
versus the developing, river height that's gonna occur pretty quickly. And it's not gonna necessarily allow for forecasting downstream,
Mhm.
or could.
Yeah, I was really impressed by, I think it really shows the value of what they do. They were able to kind of forecast, I think, 4 or 5 days out that, hey, this is really mounting up to be a significant event. They started, activating emergency response, in advance. And then the forecasts that I saw were really useful and accurate, so. But I see your point. I think it's good to continue to check the accuracy of those.
You spoke about your goal, the goal for the phosphorus.
Right.
What is it?
Oh, what is it?
What's your goal?
575 metric tons per year. That's for the entire lake. So, the TMDL is broken up by lake segment and assigned to, the New York State and Vermont State and Quebec. So it's kind of chunked up, but that's the number we're going to, yeah.
Where is it now?
Yeah, so that's a tricky question. I can say that the TMDL, when it was developed, looked at a base period of 2001 to 2010. And the kind of that base period loading was 921 metric tons. Okay, so there's a significant reduction that needs to be made to get down to that goal of, more like below 600 metric tons. That is split up again between 2 jurisdictions and a lot of different areas. But on a year-to-year basis, it's not quite as simple to calculate. So, and also there's that interannual variability I talked about. So last year or 2022 was a dry year. We had this big flood in 2023. So looking at it year by year is less useful than looking at, say, over the past 5 or 10 years. So, yeah.
So the goal is to reduce the phosphorus.
That's right.
Presumably you have estimated impacts of the various preventative controls you're putting in place. Do you have a ranking, or what's the most important thing to do? Is it to protect the rivers erosion along the tributaries, or is it more like farming and waste use and access to the water? Do you have that broken out?
Yeah, we have a lot of information on that. A lot of research has gone into what's the most effective way to reduce phosphorus over time. And a lot of it is kind of what's the lowest hanging fruit, what can we afford to do, and where are the opportunities. So a lot of the work is done in agricultural areas because they're softer landscapes and there are, management practices that can be changed or upgraded. There are, practices that can be applied that will reduce agricultural or phosphorus runoff in the landscape. So a lot of our efforts have been focused on agricultural, reducing agricultural pollution. And then we also are working on, stormwater runoff. So we call it stormwater when it's things in developed areas over parking lots and road surfaces. Traditionally, those are routed right to a storm drain, heading right to our waterways, but we're now kind of rethinking how this works and are able to implement things like we call it green stormwater infrastructure. So we're slowing down that stormwater, we're treating it in some cases, we're trying to avoid it from going into the waterways. So the state of Vermont, is responsible for implementing the TMDL. They have a whole division devoted to quantifying and tracking progress on phosphorus reductions. And they also have a system where they pay for phosphorus reductions based on the dollar per pound. So they're looking for the best opportunities to make those reductions.
So, a couple of quick questions. Are there implications to the water level of the lake still being 3 feet above what, you would say would be average?
So the lake level is relatively high right now. Typically, even when we have high levels in the summer and the fall, the winter usually the level comes down to a point where it's relatively normal. We're seeing relatively high levels right now. And we're actually convening, a webinar on this issue specifically and getting some forecasters together to talk about their predictions on, people who know more than me about what the climate indices are looking like and what the precipitation might look like in the longer term and what lake levels might be. So I think from what I understand, we're not guaranteed to have a, floody spring, but certainly it's possible just like any year. And there's still time for it to go down, before we have our spring snow melt period.
Yep, and the second associated question is, how long does it take the lake to mitigate an event like that? Or does it ever? Is there residual phosphorus that ends up being part of the permanent load in the lake?
Yeah, that's a great question. Something I was hoping to put together for tonight, but as Colleen said, I was out sick last week, so the lake is a big system and it can kind of recover from an event like this. The biggest thing we saw was just that turbidity, right? It took about 2 weeks for it to go back to normal and for that particulate phosphorus to settle out over about, 14 to 20 days or so, 2 to 3 weeks. And looking at the phosphorus concentrations is another way to look at it. We did see some spikes following the storm, but within 2 weeks, it was really back to what we normally see. And something we kind of understand, the lake, we call it one, many lakes in one, because it's such a diverse, physiographically, we have shallow bays, we have deep basins in the main lake, in the northeast arm. They behave very differently for water chemistry and lake dynamics. So the main lake, phosphorus levels can be driven by storms like this, especially the dissolved phosphorus, because the particulate phosphorus, the phosphorus that's hanging onto the sediment, will sink to the bottom and really be taken out of the game. But the dissolved phosphorus is still in that higher level and can interact with things that are growing. That's the deep basins. But for our shallow basins, the phosphorus levels are actually driven more by internal processes. So there's phosphorus kind of locked up in the sediments that are at the bottom of the lake. And those can be released, especially in the late summer and the fall. And that really drives phosphorus levels for Missisquoi Bay, St. Albans Bay, parts of the South Lake, and even the Northeast Arm or the Inland Sea, more so than storms like this. And we saw that in our monitoring data where we saw a bit of a spike. There's a lot of phosphorus coming downstream. We call it external loading coming from the watershed. It recovers within a week or two. And then those internal processes are still driving the dynamics.
So like when the lake turns over, I guess.
That's another example of an example. Yeah.
Okay. Thank you.
Sure. Yeah, maybe one more. Yeah.
I think it's interesting to say there are several different lakes within the lake. That makes a lot of sense. But there's also several different watersheds that have, from what you pointed out, very different responses.
Absolutely.
Both in the flashiness as well as the phosphorus that goes in. And I also, so I wanted to say that I got that out of your presentation. The other thing is though, that we focus on water levels as a metric. But with the climate change, we have these increased regional storms that we've seen 2011 and 2023. But we also have increased wind, which has profound implications for damage along the lake to the near shore areas in particular. And I don't know about the mixing within the lake.
Yeah.
That has impacts on that as well.
Yeah. Yeah, thanks for bringing that up. I think I've looked at there's been a few kind of analyses on wind speeds. I've seen some analyses that actually show wind speeds in the summertime and the fall are actually decreasing. But then we have wind storms, where more persistent low pressure systems, where we have these episodic high wind events. And that's what you care about when you have the damages, right? Not what's happening throughout the summer, but when you have those big storms. So Yeah, that's a great point, and I don't have, an analysis to prepare. to
And you
talk
wouldn't
about,
see
but-
those impacts if you're looking only at riverine systems,
Sure,
because winds don't have as much impact for most riverine systems.
right,
But it's just fascinating, that we're learning more and the complexity of these systems.
absolutely. All right, I think we'll end it there.
See, great,
Okay,
thanks, Matt.
all right, thanks.